This is the Year 8 motion and pressure reverse to classroom. So it's getting the facts or a number of facts into your head before you actually go into the unit itself. So then you'll find the unit easier. This is the snaky diagram. So you're going to be doing about speed, motion, more motion, pressure in gases, pressure in solids, and potentially moments, even though in this reverse to classroom we won't talk about moments. Right, so one of the formulas that we're going to use in this is speed equals distance divided by time. Speed is measured in meters per second, distance in meters, time in seconds. Okay, common kind of formula that is then used. Now, what I've got on here is I've got two graphs, and they're kind of exactly the same graphs, but I've just put them in then just to sort of explain exactly what's going to be going on. First thing you do is look at the time, so you know it's time. You look down the side, you know it's then in distance, and you know it's in kilometres. The question will be is what is happening at A. A is going from there to there, and it's going at a constant speed. Right, and you know it's going at a constant speed because it's a straight line. Then, the blue line, which is B, think about exactly what it's doing. At B, what it's doing is it going, or is at, 31 kilometres. If it's at 31 kilometres away and it doesn't change, that means the blue line is then stationary. The green line, I'll do it in blue, right? The green line is again a straight line going up, and that means it is going at a constant speed, but it's faster constant speed than A. The final one, D, is a negative gradient, right, but it's still going at a constant speed, and ultimately it ends up exactly back at the start. Now, what you can do is if you've got a distance time graph, this is a slightly different graph, but I know it's a distance time graph because it's got time and it's got distance travelled, this time in meters. What you can do is you can calculate the speed. Speed equals distance divided by time. So I can then work out, right, for this line here, the speed the object actually been going at. So I can look here and I can see that my distance is 100 meters. My time is 30 seconds. So my speed is 100 divided by 30 in meters per second. So the gradient is the speed of the object. This is then a speed time graph where what we're going to do is we're going to talk about what's happening. Now it's different to the other one, even though it's got time there, it's now got velocity up the side. So what you've got to do now is you've got to think about what's happening on the red line there. So I'm just going to put the red line there. On that red line there, as time goes on, its speed increases. So therefore, it is going at it's not constant, it is accelerating. Because what it's doing, it's getting faster. And you could say it's going at a more constant acceleration. B is then the one that kind of gets people a little bit, because people say, oh, it's stationary. Do your little line across there, and what you'll see is it's going at 3 meters per second. Therefore, if it's going at 3 meters per second, it must be going at a constant speed. So it's not stationary. The black line, right, this is then the black line is accelerating again, but it's accelerating faster than the red line. And the green line is then, let's do a green line. The green line, because it's going from a 6 meters per second down to 0 meters per second, it is decelerating. Now these are a few like little examples of graphs. All right, on a distance time graph, right, when it's horizontal like that, that means it's stopped, stationary. On a speed time graph, it's right at the bottom. This means it's going at no speed at all. Constant speed is a straight line like that on a distance time graph. On a speed time graph, it's going along at 8 meters per second, which is a constant speed. On a distance time graph, if it's accelerating, it curves. On a speed time graph, it's accelerating when it's going on a straight line like that. Pressure. Here's a second equation on this. Pressure equals force divided by area. Pressure, what they do is they go down and there's a lot of water above them and the pressure builds up on them. The question over here then to the right hand side is, who hurts the most? Somebody wearing stilettos or somebody wearing big boots? Which one will hurt the most? If you actually go through the calculations, because of the end of the actual shoe there, where all the force is then into one very small area, that can actually cause a lot more damage and a lot more pressure than a big heavy boot. Pressure in liquids, two little diagrams. Right, so what I've got is I've got a bottle that's open at the top, all the holes around the outside. Each one of those little kind of tinkly bits there, right, should be exactly the same because the pressure from above is identical for each one of those holes. For the second example, the pressure is less at the top, so therefore the little dribble coming out is gradually going to get further and further away because of the amount of pressure in the liquids. In the collapsing can experiment, when you first start with this, what you've got is you've got pressure from the inside pushing outwards, you've got pressure on the outside pushing in, and both those pressures are identical. If I take away all of the air from the inside, that means then there'll be no pressure from the inside. So the outside pressures are much greater, which then means that the can will then get squashed, or it will collapse. Now here's the 5 questions. What is the formula of pressure with units? If a line is horizontal, right, so a distance time graph, time, distance, if a line is horizontal, what does it mean? If a line is horizontal on a velocity time graph, what does that mean? What's the equation for speed with units? What makes the can collapse? Now I like this unit, right? So what you've got graphs that then what you need to do is you need to be able to understand. You've got equations, so then you've got to be able to work things out. You've got units that then go along with them. So for example, pressure is pascals, force is newtons, etc., etc. So it's a good introductory physics unit.